Okay, hello to everybody. I'm very happy to be here. So I'll be talking basically about the partnership. I'll be talking about health again. I'll be talking about the partnership that we have at Polytechnique with CNAM. So I guess most of you know Ecole Polytechnique. It's an engineering school. Now, few of you maybe know CNAM. So let me tell you what CNAM is about and what is SMDS. CNAM is Caisse Nationale d'Assurance Maladie. It's the French, it's the main institution that manage reimbursements of healthcare in France. Okay? Now, the good news is that in France, we basically reimburse everything, every healthcare. Okay? So that's good news for individuals, of course, but that's also good news for scientists like me, because then you have this huge database, which is called SMDS, Système National des Données de Santé, which gathers all the reimbursements of all the individuals in France. That's more than 65 million people in one database. It's an electronic health record database. It's one of the biggest in the world, okay? So it contains all reimbursement of pharmacy, hospital, doctors, and you have quantities, diagnosis, and so on. It's more than 200 terabytes of data, okay? So we're talking about big data. Of course, this is an amazing source of information. So let me give you some examples. One example with some impact on health, of course, pharmaco epidemiology. So this was the database that was used by CNAM. They have statisticians there to make the link between third-generation pills and the risk of pulmonary embolism. Okay? And that was the same database that also confirmed that it's likely that there is a problem with the Mediator medication. You know, Mediator is likely to kill people, and that was confirmed by the statisticians at CNAM using this database. So when we think about using this database, we think about health, but you should also think about applications on economy. This is health. Public health is the first French budget. It's more than 200 billion a year. Okay, so there are a lot of potential impact on economy. For instance, with this database, you can identify all the people with a given pathology, so you can know how much cost this pathology to the nation. Okay, now if you identify, let's say, all the people with diabetes, then if you're able to do clustering on these health pathways, then it means you are able to identify typical pathways. So if you have typical pathways, you know which ones are the best for health, or that are curing the best, and which ones cost the least, okay? So this is like major impact for economy. This is very hard. Doing clustering on pathways, this is not an easy subject, okay? But if we could do it, then that would be really, really nice. So we have this partnership. We are working on this database. We've been working now for almost 4 years. So we started in 2015, and we renewed the partnership for 3 years. So we have 2.5 years left. We have a pretty big team for an academic team. There are up to 5 developers. When I'm saying developers, like Scala, Spark, C++, Python. We have actually 2 PhDs, 2 postdocs. These are full-time people. And we are about 3-4 researchers part-time working on that. This is a big team, but this is too small. So we are recruiting. So please send me emails. Okay, if you are interested to work with us, we are recruiting. So what have we been working on? So we've been working on this pharmacoepidemiology thing I was telling you about, finding drugs that have adverse effects, like Mediator, which are killing people, that are on the markets. I will tell you about the first result we had last December, developing a screening algorithm. I'll go into more details later. We're also currently working on fraud detection. So this is not like fraud detection like you have in banks. It's not like about people being reimbursed and they should not be reimbursed or stuff like that. It's fraud detection about finding networks of doctors who are basically drug dealers. Okay? This is the kind of fraud we're looking at. And we're working on health pathways. So it's like what I was telling you about, like trying to cluster them And actually, we're now working on a visualization tool that would be able to visualize like the 3 million pathways of the diabetic people and to interact with it. This is there is no such a software on the market right now to be able to work with 3 million pathways at the same time. So we're working on that. Now, when we started 4 years ago, we had a big problem, is that the SMDS infrastructure is really not at all suited for analytics. It's suited for reimbursement. It works pretty well. I mean, we're all very happy because there is no problem about reimbursement. But if you try to do analytics on the current infrastructure, it's a nightmare. So we had to change the whole infrastructure. That was huge work. And we started really to have something working after 2 years of work, okay? So this is just a sum up of what we have been doing for the first 2 years. So we didn't work on the whole database at once, okay, because that's like 250 terabytes, that would be too much. So right now we are able to work on, let's say, 40 terabytes. So we've been redesigning the database infrastructure. You have to imagine that the actual SMDS is a relational database, Oracle, it's owned by Oracle, and it has more than 800 tables, okay? And you have like 20 tables which are gigantic, and one table which has more than 1 billion lines, and it's not centered on the individual, it's centered on the reimbursement. So whenever you get something reimbursed, you have one line on this huge table, and that is linked to like the 800 tables. Okay, so if you want to just have the pathway of one person, that's a nightmare. It's a request on SQL, which is a nightmare to write. Okay, so we had to flatten it. Actually, we just put it in Parquet format using an HDFS cluster. So that's the second part. We had to update the infrastructure, the computer infrastructure of the SMDS, because they only have Exadata Oracle computers. So we have now HDFS cluster where we're doing the flattening and where we are also doing the featuring for the machine learning algorithms that will run. And at the very end, they were able, I mean, SMDS, you're only able to work with SAS, basically. So that's not the kind of tool that people are using in this room, I guess. So we had also to build infrastructure for that, and we're doing basically C++, Python, or R. So this is a very important part of the work. I don't know if you heard about it. It's on the social networks a little bit. There will be a health data hub in France. This is a very big project that was pitched by President Macron when Villani finished the report. It should start, building this hub should start in January. It should open in June. So the idea is to have access to the SMDS on the modern infrastructure. So this is like, what we did is like a prefiguration of what the hub will be, okay? And then ultimately it will link to all the clinical data of all the hospitals, all the public hospitals. Okay, so this is, if we succeed to do that, we'll have the best health database in the world. Okay, if we succeed to have like APHP, all the public hospitals data linked to the SMDS database on the modern infrastructure, with like a marketplace where startups could go and access the data and so on, that will be like a big hit. It's a challenge. I hope we'll succeed, but we have money for it, and it's a government decision, so it's likely that we'll succeed. So let me tell you a little bit about the algorithm we've been working on pharmacoepidemiology. Today, if you're asking a question, does the mediator is likely to kill people or not, what do you have to do? You have to ask experts of the mediator. What does it mean to be exposed to mediator? They will say, okay, you have to take it twice within 3 months, and so on and so on. Okay, so they are discussing. Once they decided what it means to be exposed to mediator, you would do an extract of the database, and then you have problems of realignment of the various pathways of the people. So you do some data preparation, which is not that easy to do. You need experts for that. And then you run hypothesis validation, which is the standard in biostatistics today. It's working really well. It will give you an answer with an error bar, of course, with a p-value. Okay, so it's survival analysis, basically, for those who knows. Okay. Now, the problem is that the whole pipeline, if you do it in a clean way, can take several months with experts. So this is for one question. Okay, so the idea was to develop an algorithm which would run before this thing, okay, which would be able to take into account a lot of medications and several adverse effects, okay, and that will be able to do some screening, okay, saying, oh, you should look more carefully to this, and these drugs. And then we would run the regular biostatistic pipeline on each of the drugs, okay? So that was the idea. So so we developed such an algorithm in order to test it. That would have been totally crazy to test it on real case, okay? Because we had to test the whole pipeline we developed, the whole infrastructure, and then this application. So the pilot project was about finding again a medication that was found in 2011 and that was taken out from the market. That was pioglitazone, anti-diabetics. So we detected, without any preparation of the data, or hardly any preparation of the cohort, with no experts, we have an algorithm which is able to detect among 10 medications, pioglitazone as a problematic drug, because it increases the risk of bladder cancer. So that was the success we had last December. So Mathieu told me I should put math but I haven't seen any math in the previous talks. So I put some math. I hope you're okay with math. So just the general framework is counting processes. I'll go fast on the math, okay? It's counting processes. Basically, you count the number of times you have the adverse effects. Okay, this is the counting processes. You discretize time. You have features which can be depending on time. When did you take which drug? And features that are not depending on time, like the age of the person and stuff like that. So we take into account all these features. And the model we have is what you see at the top of the slide, which is the intensity at a given time of the counting process, meaning the probability of the adverse effect to appear is regressing on all the features, the time-dependent features and the non-time-dependent features. And you have a translation invariant parameterization, which is used. So basically, it means that we don't have any realignment in time, okay? And this is a strong improvement compared to the literature, because in the literature, as I told you, basically you deal with just one medication at once, and here we're able to deal with several ones. Okay, so ultimately, basically, you have a multinomial law, and you have to estimate the parameters. Now, so we want to find, the parameters are what? The parameters will tell you, when you take a drug, what will be the effect of taking this drug through time. Okay, this is basically the output of the algorithm. Okay, now we did some penalization because we don't want the output to be totally irregular. The output is not likely to be like something like that. Like I don't know, like in 1 month is going to be something terrible will happen, and then 2 months nothing can happen, and 3 months again can happen. You know, it has to be regular. So we did some penalization. We use group total variation that you can see at the bottom here, at the bottom right. So these are the different classes of anti-diabetics. This is the lag in months. So basically, you have 0 is the time when you took the medication, okay? And these are the parameters that tell you how is the effect. So when it's red, it means it increases the risk of bladder cancer, okay? And so what you see is that for pioglitazone, after 2 years of exposition, then you have a really strong risk of bladder cancer that you don't see for other medications. So that was the first success we had. So now we're moving on true application. We're working on true applications. So when we were working on diabetics, we're working on 2.5 million people. There are 2.5 million diabetic people in France. There are 400 new cases each day. Okay? That's just to scare you a little bit. So now we're scaling up. Okay? We're working on old people, senior people, so that's 12 million people above 65 years old. And we're working on a much larger class of medication. We have 400 drugs, more than 400 drugs. And we're looking for adverse effects, which is fall of the person, fractures. Okay, so all people that falls. Okay, and we try to understand among these 400 drugs which ones are increasing the risk of falling for all the person. So we're gonna have results soon, I guess. If I had results, I would not have been allowed to talk about them, of course, because I cannot tell you the name of the medications that are problematic. So otherwise, there is a lot of money to do on stock markets about that. So we're working also on generalizing the algorithm, being multitask, so many adverse events at the same time. So there are a lot of work to be done to improve these kind of algorithms and to make it full scale. Ideally, we can dream, but this is a dream, of an algorithm that would run automatically on the SMDS and that will identify some problematic medication that people would have to look more carefully at. Okay, that's a dream, but I guess this is a dream that can become true. So more applications to come, as I told you. I think the health pathway is a very important application, visualization, clustering. Actually, I don't know about the other talks, but I know about a lot of large companies in France, and I know a lot about various applications. I know that everybody is obsessed, like if you're talking with marketing, gaming companies and so on, they are all obsessed with like CRM, pathways, the pathways thing, consumer journey. This is everybody's obsessed by that. Trying to do some clustering on that, trying to do some machine learning on these structures. This is a major challenge. This is very hard, and it can have applications everywhere, really everywhere. And CRM is, of course, one of them. I will end by an advertising on the toolbox we're using at the very end, where we're doing the machine learning. Okay, this is a toolbox that is called. This is open source. It's called TICK, T-I-C-K. It's a machine learning toolbox. It's highly optimized. We're working with Intel engineers that are coming regularly to our place and that are optimizing like all the loops. It's C++, directly programmed in C++, and then with the Python layer. And it's basically, it's specialized on statistical learning for time-dependent models. Okay, so if you have time-dependent models, then you have a lot of algorithms that are already coded, and it's currently used a lot by the banks. Okay, because there is everything about Hox processes. If you're interested about Hox processes, this is like the biggest library about Hox processes. So a lot of people are using it, and of course, health. This is the website, and I'm done. Thank you very much.